Welcome to an interactive course designed to validate and improve our knowledge of heat treatment. The topic of this course is the explanation of the issue of hardness measurement. Hardness is most often defined as a mechanical property, expressing the resistance of a material to the penetration of a geometrically defined indenter at a given temperature. It depends on many material properties, but primarily on the elastic properties. Modulus of elasticity EE of the tested material, and on its plasticity. In terms of hardness values, each material therefore behaves differently. However, since the design of various assemblies often also depends on the difference in hardness, it is a constant effort to compare these values and therefore to measure them. The left picture shows a comparison of the behavior of different materials during a tensile test, and when determining the Young's modulus of elasticity, and the right one shows a comparison of hardness for different materials and different temperatures. The differences are enormous. And why is this so? Every material, metallic or non-metallic, has its own specific properties. These properties are influenced by the structure of the material defined by the type of atomic bonding, the type of crystal lattice, and the amount of lattice defects such as vacancy, dislocations, or other structure inhomogeneities. Hardness is further influenced by the microstructure of the material, given in particular by grain size, the degree of morphological unevenness, the amount and shape of impurities in the structure, internal stresses in the material caused by forming, uneven cooling or phase transformations. Temperature also has a great influence on the measurement result, which also significantly affects the elastic, plastic, and strength characteristics of the material, and thus the measured values of its hardness. From the above, it can be concluded that hardness measurement is the basic method for evaluating the properties of parts and materials, and is also the most frequently measured, usually the only quantity by which we evaluate the result of heat treatment immediately after its execution. Correct hardness measurement is therefore decisive for assessing the correctness of the heat treatment performed by us. It is in the interest of every heat treater to measure hardness correctly, without unnecessary errors, and as accurately as possible. Therefore, we should know more about this field of measurement. Hardness measurement is carried out according to various methods. We will describe these methods on next slides. Even though the measured values have a certain relationship to the strength of the material, these are values that are usually stated dimensionless, only stating the given method of measurement or scale. Hardness measurement methods can be divided as follows: into static indentation methods, which are used with names such as hardness, according to Brinell, Rockwell, Vickers, or Knoop, according to the type of indenting body. In practice, however, we also encounter other measurement methods that are not based on the penetration of a body into the tested material. These are primarily dynamic reflection methods, where the surface of the material is not acted upon by a static, gradually increasing force, but the load is applied dynamically, suddenly. And last but not least, ultrasonic methods, based on the oscillation of a rod with a Vickers indentor according to ASTM 1038-05. The first of the basic methods of measuring hardness is the Brinell method. This involves pressing a steel or tungsten carbide ball with a diameter of 1, 2.5, 5 or 10 millimeters into the test specimen. The diameter of the indentation is a criterion of hardness. For softer materials, a load of 1 to 500 kilograms is used. For harder materials, 3,000 kilograms. The drawing marking of the Brinell hardness requirement always contains 3 data. For example, HBW 10-3000 or HBS 5-250. In this marking, the abbreviation HB represents the Brinell measurement method, W means that the ball is made of tungsten carbide. S, that the ball is made of steel. The values 10 or 5 then express the diameter of the ball in millimeters, and 3000 or 250 indicates the load on the ball when measuring in kilograms. This method is governed by the international standards, ISO 6506. Part 1 describes the Brinell hardness test method. Part 2 describes the verification and calibration of testing machines, and Part 3 describes the calibration of reference blocks. The relevant American standard is ASTM E10. The Brinell method is usually used for hardened and tempered materials with lower hardness, but can be used up to the equivalent of 57 HRC. Although this method was specifically developed for measuring the hardness of castings or forgings with poor surface quality, paradoxically today, it is the most accurate method for measuring the surface hardness of large parts such as dies or mold inserts, as it eliminates surface heterogeneity due to the high contact force. However, this requires a portal hardness tester arrangement in many cases, taking into account the size of the parts being measured. Hardness values are calculated from the top of the ball that the indenter pushes into the material. In the formula, the value 2F represents twice the pressing force. The capital letter D is the diameter of the indented ball, and the lowercase d is the diameter of the indentation in the surface of the measured piece. This value is the average of two measurements of the indentation size in directions perpendicular to each other. In practice, however, we do not calculate anything like this. There are tables where, according to the measured indentation diameter, we get directly to the hardness value in Brinell units. One possible source is the table given in the ASTM E10 standard. However, we do not always have an image of the indentation in such a way that we can simply read it. In the case of a hardened material, we run into the problem of the material bulging around the indentation. This can be clearly seen in this picture. Reading the diameter is then difficult, and if we are to do it correctly, it requires at least good lighting. The minimum thickness of the test specimen must be at least 10 times the depth of the indentation in order to cause plastic deformation only in the tested material. Everything can be seen in this table. For example, for a compact body when measuring Brinell hardness with a load of 3,000 kilograms, the thickness of the part must be at least 9.6 millimeters, with an assumed minimum hardness of 100 Brinell units. To avoid influencing the result by measuring at the edge of the sample or by material straying tenning around the previous indentation, it is necessary to maintain a distance of 3 times the ball diameter for soft materials and 2.5 times for hard materials between two indentations. Hardness reference blocks intended for calibrating the hardness tester are usually already prepared for this case and have an indicated grid where the test indentations can be placed. Measurement tests should be performed at an ambient temperature of 23 ± 5 degrees Celsius. In the next section, we will look at the Rockwell hardness measurement method. This method no longer measures the area of the indentation, but the depth to which the indenter, diamond, cone, or ball penetrates. Since the indenter impressions are relatively small, the inspection and its result are sensitive to a number of influences. For the Rockwell method, there is again a set of 3 basic standards. Part 1, Test Method. Part 2, Verification and Calibration of Testing Machines and Indenters. And Part 3, Calibration of Reference Blocks. Similar specifications are in the ASTM E18 standard. All variants of Rockwell hardness measurement are also described in these standards. There are a whole range of them. This can be seen in this table. The classic Rockwell A, Rockwell C, and Rockwell D measurement methods use a diamond cone, while the others use a 1/16 or 1/8 inch tungsten carbide ball. The methods also differ in the load used from 60 to 150 kilograms. The highest value is associated with the most widely used HRC measurement method, but it is also used for the HRGW method. The letter W has the same meaning as in the Brinell method. It is a tungsten carbide ball. Another group of Rockwell measurements are surface methods, so-called super Rockwell. The loads used are 15, 30, and 45 kilograms. The HR15N, HR30N, and HR45N methods use a diamond cone, while the HR15TW, HR30TW, and HR45TW methods use a tungsten carbide ball with a diameter of 1/16 inch. Each of the Rockwell measurement methods has its applicability for a certain group of materials. As a rough guide, we can say that the Rockwell A method is intended for sintered carbides, thin steels, and possibly hardened steels. The Rockwell B method is for copper alloys, mild steels, aluminum alloys, and ductile irons, while the Rockwell C method is for steels, hard, cast irons, possibly hardened steels, and other metals harder than 100 HRB. The Rockwell D method is used for steel sheets and possibly for medium-hard steels or pearlitic malleable cast irons. The designer prescribes which method will be used on the drawing in accordance with ISO 15787. The hardening shop is only responsible for carrying out the measurement according to the regulation and ensuring that the requirement and reality are in line. Since the Rockwell measurement method depends on many parameters, they need to be taken into account when making the actual measurement. This concerns the quality of the surface, the fixation of the parts for measurement on the hardness tester and their stability, or the perpendicularity of the indenter to the measured surface. So it is not as simple as it seems. Hardness testers are supplied with a number of accessories, often special, which allow us to measure even parts with complex shapes correctly. However, we have to prepare the actual surface for measurement ourselves. If the hardness calibration blocks are polished, with a surface roughness of 0.1, then for measurements on real parts we will need a ground surface with a roughness of 0.4. The table of surface quality requirements for individual measurement methods is shown in this figure. Brinell is the best, Vickers is the worst. In practice, an angle grinder with sandpaper of the appropriate grain size is best suited. In measurements using the Rockwell method, measuring cylindrical surfaces is a big problem. The measured values will not exactly correspond to the actual hardness. Therefore, a correction factor is introduced, which is implemented directly into the hardness tester software on some hardness testers. However, for older ones, the correction factor must be used from this table. It can be seen that only above a diameter of 25 millimeters does the measurement error fall below 0.5 HRC or 1 HRC. Since hardness measurement does not have absolute accuracy, the resulting values must be calculated as the average of at least 3 measurements in accordance with the ISO 6508 standard. When evaluating, it is also necessary to take into account the accuracy limits of the measurement methods. This figure shows that for the HRC method, it is plus or minus 1.5 Rockwell. However, it is important to note that the value of plus or minus 1.5 HRC represents a parameter of measurement reproducibility and includes natural variance when using different hardness testers, operators, and conditions. Therefore, if we want supervisory control of our measurements, we must take this tolerance into account. Therefore, the basic rule applies to our measurements. The correct value is not what I want, but what I measured. Another method of measuring hardness is the Vickers method. It is based on indenting a pyramid with an apex angle of 136 degrees into the measured material. The measure of hardness is the size of the indentation diagonal. The indenter load is very diverse. for macro hardness from 1 to 100 kilograms, for micro hardness from 0.01 to 1 kilogram. The set of standards for the Vickers method is similar to the Brinell or Rockwell methods. Part 1. Test method. Part 2. Verification and calibration of testing machines and indenters. And Part 3. Calibration of reference blocks. Similarly, the American standard ASTME 92, standard test methods for Vickers and Knoop, and for micro hardness, ASTME 384, standard test method for micro indentation, hardness of materials. Micro hardness measurement, according to Vickers, is preferably used to measure diffusion profiles after carburizing or nitriding. Instruments for measuring Vickers hardness or micro hardness are usually variable in terms of the load applied to the indenter. However, not all types of measurements are permissible. From this table for nitriding layers, it can be seen that the smaller the depth of the affected layer and the softer the material, the lower the load must be used. The extreme example is the measurement of thin PVD layers, where up to a coating thickness of 10 microns, only a load of up to 10 grams can be used. The same is true of measurement accuracy. The lower the load, the lower the accuracy. The table shows that at low loads, the measurement deviation can be up to 10%. At high loads, it can be only 2%. This must also be taken into account when evaluating our measurement. Just to give you an idea, 540 HV 0.2 measurement has a variance of plus minus 9.52%, which is 540 plus minus 51 HV 0.2. 540 HV 1 measurement has a variance of plus minus 5.08%, which is 540 plus minus 27 HV1. 540 HV 10 measurement has a variance of plus minus 3%, which is 540 plus minus 16 HV10. As with the previous methods, the distance of the indentation from the edge or from another indentation must be at least 3 times the diagonal of the indentation for soft materials and 2.5 times for hard materials. Otherwise, there is a risk that we will measure material strengthened by plastic deformation from the previous indentation. To avoid this phenomenon, we can buy hardness calibration blocks with a grid already created. The quality of the surface for measurement has already been mentioned. For the Vickers method, it is a roughness of less than 0.4. According to this table, sandpaper with a grain size of at least 400 and finer is needed. An alternative for measuring surface hardness is the Knoop method. It is used primarily for thin materials, thin layers, or brittle materials. The Knoop micro hardness test is prescribed by the ISO 4545 standard, where the measurement itself is described in Part 1. In Part 2, there is a description of the calibration of the instruments, and finally, in Part 3, there is a description of the calibration of the reference blocks. The indenter for Knoop measurement is a diamond pyramid with a rhombic base. The rhombic indentation created by this indenter has a ratio of diagonal lengths of 1 to 7. The load range, according to the standard, is from 25 grams to 3.6 kilograms. In this method, the hardness of the material is evaluated only on the basis of the longer diagonal. This diagonal is much longer than in the Vickers method at the same load, so the reading is significantly more accurate, which has a positive impact on the resulting accuracy of the obtained hardness value. Thanks to its very shallow indentations, only 1/30 of the length of the longer diagonal, the method is suitable for measuring the hardness of thin coatings, metal foils, and thin sheets, or thin hardened surface layers. Due to the small depth of the indentations, the method is very demanding on the quality of the tested surface, on the roughness and flatness, and the parallelism of the measured surface with the base. The format for recording the measurement result is, for example, 640 HK 0.120. This means that a hardness of 640 according to Knoop is required. HK represents the Knoop measurement method. 0.1 is the approximate value of the equivalent load used in kilograms, and 20 is the time of application of the test load in seconds. This value is given if it does not lie in the prescribed range of 10 to 15 seconds. Again, the measurement cannot be performed without restrictions. In this figure, the minimum distances of the indentation from the edges and from each other are shown. What do all methods have in common? First of all, the calibration of the instruments. All hardness testers must be periodically linked to a higher standard and calibrated. For the aerospace industry, every 6 months, once a year for other applications, and once every 3 months if the operation operates according to AMS 2759, which is an American standard called Heat Treatment of Steel Parts, General Requirements. Each calibrated instrument must be labeled with a calibration label, and the date of the next calibration must have a certificate of conformity, a calibration sheet for the contractual scope of the instrument, and a record of preventive maintenance. In addition, hardness testers require daily calibration or calibration before first use. The calibration record is entered in the hardness tester logbook. Alternatively, calibration is also possible for each work shift, which applies mainly to the aerospace industry. Daily calibration should be performed for one measurement range, if the measurements actually performed correspond to this, or for multiple measurement ranges according to the expected reality. In addition to the periodic calibration of a commonly used instrument, hardness testers must be certified by an authorized person after purchase, after each major repair, after moving, or if they show inconsistent data. The instrument must also be recalibrated after each change of indenter or after the weight is replaced. An entry must be made in the instrument logbook about the replacement of both elements. Each instrument must be clearly identifiable, and an unfit hardness tester must be marked and secured. Portable hardness testers must comply with ASTM E110. Calibration of the instrument in an uncontrolled temperature environment should be carried out at temperatures between 10 and 35 degrees Celsius, or it should be declared that measurements outside this temperature range do not affect the result. Another problem with hardness measurements are the calibration blocks. These must also be identifiable, including a record of the date of first use until the time of disposal. The permitted lifetime of a calibration block is 5 years. Then it must be disposed of. Before calibrating the instrument, it is recommended to perform 2 measurements on the calibration blocks. Invalid indentation must be marked on the block, and the block cannot be used for loads other than those for which they were calibrated. Calibration blocks must not be renewed, for example by grinding. Diamond indenters must be checked continuously, and those that are damaged must be discarded. Replacement of diamond indenter is mandatory after 2 years regardless of damage. In practice, it is necessary to check the indenters daily or before the first measurement. This applies to both diamond indenters and balls. Working with measured values is also important. It is understood from the production documentation that each test is performed only once. If multiple tests are to be performed, their specifications must be part of the sales order, production instructions, or quality order. Each test can have multiple measurement values. The result must be recorded as a value or range of values. It must not be just the average. The number of measurements is in this table. The description of the measurement result should also include the correction factor used for the hardness tester, hardness reference blocks, or the correction factor for the measured radius. If the test starts immediately after calibration and the first value is lower than required due to the part settling on the device, This value can be ignored for the measurement results. If unit conversion is to be performed, then only in accordance with ASTM E140 or ISO 18265. Unit conversion, automatically performed on hardness testers, is not permitted, even if it is in accordance with the above standards. Conversion between units of hardness and strength of materials in megapascals can only be used as an approximate value. In case of searching for an exact value in megapascals, tensile tests need to be performed. The conversion data must be in brackets. The use of alternative measurement methods is possible only with the consent of the customer. In the production process of the heat treatment plant, the traceability of the measured values and their relationship to the measuring instrument must be ensured. For each calibration of the instrument, the accuracy and deviation of the measurement according to this formula should be evaluated, where the hardness tester deviation is the difference between the average measured value and the hardness value on the hardness reference block. The measurement accuracy is then determined as the ratio of the measurement deviation to the hardness value on the reference block, and this accuracy should not be worse than 3%. When prescribing hardness measurements or evaluating the results, it is necessary to adhere to the hardness prescription format or the measured value format. As already mentioned, hardness values do not have units, and how we should interpret them is precisely tied to this description format. And if we want to compare the measurement results with each other, it is difficult to find a match in the result between, for example, HV100 and HV1. In order to maintain the correct terminology and at the same time limit inconsistent interpretations of what the hardness prescription represents, we must adhere to the following rules. For Rockwell C, the values are written as 61.5 HRC, and not, for example, 61.5 RC. For the surface Rockwell, the value is written as 91.3 HR15N, not as 91.3 15N. For the Rockwell B method with a tungsten carbide ball, the value is indicated as 98 HRBW. For the Vickers method, we will write 675 HV30, not 675 HV. And for the Brinell method, with a 10 mm diameter tungsten carbide ball and a load of 3,000 kilograms, then as 325 HBW10. 3,000, not 325 HB. Although hardness measurement is a seemingly simple discipline, it is actually very demanding with regard to the need to ensure reproducibility and traceability of measurements. Each instrument should have its own calibration record and traceability to higher standards. The hardness measuring instrument should also include a hardness tester logbook, which contains records of daily or shift calibration, maintenance of the hardness tester, or replacement of the indenter or weight. Nowadays, however, many of these records are handled directly in the ERP system in electronic form, as are individual measurements. The records should enable full traceability of the measurement, which means that the measurement was performed on a validated instrument, when and by whom the measurement was performed, and with what result. If the hardness tester logbook is kept in electronic form in the ERP system, it must be ensured that a hardness tester with an expired calibration period or a hardness tester that has been discarded for any other reason cannot be assigned to the given measurement. Values should be given in the correct format, and according to ASTM E29 to a maximum of 1 decimal place. According to this standard, Section 6, values can be rounded, as follows according to the table. Values after the decimal point less than 5 are rounded down to the nearest whole number. Values greater than 5 are rounded up. If the measurement result after the decimal point is 5, the measured value can be rounded up or down to the nearest whole number. The qualification of the personnel is important for hardness measurements in heat treatment operations. There are significant requirements for these, especially if the operation wants to work under NADCAP for the aerospace industry. These personnel are required to have knowledge of the measurement methods, practical skills, to be regularly trained, and to have their knowledge regularly reviewed and tested. They are usually divided into Level 1 personnel, who carry out measurements at the general industry level, where there are no special rules as in aerospace production. In addition to the measurement itself, they must be familiar with the preparation of parts and surfaces for measurement, with the operation of hardness measuring instruments, and with specific measurement methods. They must be trained to carry out daily calibration or calibration before the first measurement. In addition, they must have basic knowledge of heat treatment. Level 2 personnel are persons who can train Level 1 personnel, are able to resolve nonconformities, and have, where appropriate, certification for the aerospace industry. In addition, both of these categories must undergo a medically certified vision test once a year. This is carried out according to the Jaeger Test Table Number 1, in Time New Roman N4 font, from a distance of 30 centimeters, and at least one eye must meet these parameters. Every operation working under NADCAP must have at least one person in this category. The last category is Level 3, where the qualification requirements are already high. These workers must meet the qualification requirements for metallurgy and heat treatment, must have at least 5 years of experience in a quality position, metallography or a similar position related to the measurement of quantities, and must be able to organize and train all workers at levels 1 and 2. And what are the most common errors when measuring hardness? Here is a list of them, but it is certainly not complete. Ambient temperature changes during measurement, vibration during measurement, impurities on the surface of both the sample and the indenter, poor sample surface preparation, insufficiently polished measuring surface or incorrectly clamped, insufficient grinding of the surface layer, measurement with inappropriate load, worker fatigue or visual impairment, insufficient knowledge of how to operate the device, hardness measurement in the wrong place, ignoring daily calibration, measuring with a damaged indenter or ball, hardness determination from insufficient number of indentations, incorrect conversion of measured values, or missing records. Do you also think that there are a lot of errors? But they are far from all. That is why such great emphasis is placed on the qualification of personnel. What we really measure are values that can have negative impacts on the actual and real physical properties of the part after heat treatment. However, these values, if measured incorrectly, can also have significant legal consequences because they are part of the contract between the customer and the heat treater. Incorrectly measured values can then constitute a violation of the provisions of the contract. The hardness measurement course is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive, and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to SCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a permanent license for €200 per course. The compressed zip file will be 50 to 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0 on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system LMS that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, or even at home. And you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.